Oh, well, I got to see the pass go, Nate.
Oh, okay.
All right, ready to talk? All right, sphere. I had asked you to go to your formula sheet for surface area of a sphere, but it's not on there. This is the one and only one you guys have to remember for Friday. Let me just introduce you to a sphere. I just draw it with the circle, the equator, and the dotted line in the back for what we can't see. The only thing you need for a sphere, and you'll see this in the formulas when we write them down, is the radius. That's the only thing you'll need, is the radius. All right? So surface area, this is not on the formula sheet. So we may want to just make a note, hey, not on formula sheet. This is the one is your only responsibility. Not on the formula sheet. You want to know what it is? 4 circles. 4 circles. 4 pi r squared. So you do have circle. All it is times 4. All right, sphere, 4 circles. All right, so let's do it. So 4 pi r squared. The circumference of a rubber ball, we're assuming is in the shape of the sphere, is 20 pi. What's the surface area? The only thing you guys need to find surface area and volume coming up is radius. If you know what the radius is, you can find surface area or volume. I don't know radius yet, but I do know, take a look, circumference is 20 pi. So I need you to go back, not a unit 11, unit 10. What was the circumference formula? Circumference, you know what, Spence?
Pi d.
Pi d, all right. So let's start there. Circumference equals pi d. And we are very knowledgeable in here. Is if you find the diameter, you know the radius. So the circumference, 20 pi, equals pi d. All right, what's going to happen to those pi's on each side? Let's talk. 13 pi's on each side, Charlie. Yes, they will. And there you go. There's your diameter, is 20. What about your radius then? Ooh, 9 radius. What do we have? 10. Yep, so radius equals 10. Now we can do surface area. So surface area, 4 pi r squared. Can we just leave it in terms of pi? So we don't have to really go to the calc, I hope. So 4 pi 10 squared. Just let's leave this in terms of pi. All right, go ahead. Leave it in terms of pi for me. 9, again. 400 pi. And if you are putting units, remember, whoa, I know we're in volume, but we just found surface area. So make sure if you're going to put units, this would be centimeters squared, right? Because it's area. So we're good. Surface area, 4 circles, 4 pi r squared. All right, what about the volume of a sphere now? You can go look that up yourself now. Volume of a sphere, hook me up. Volume of a sphere. 11 when you're ready there, Kelsey, on your formula sheet.
4/3
Woo!
pi r cubed.
Woo. Good thing we're given that one. And again, you guys see the only thing you need? Radius. That's it, right? Radius. That's all I need. Ooh, the volume of a sphere is 36 pi. What's its surface area? Woo-hoo. What's the only value you need? Radius, right? I can get that from the volume formula. So the volume, 4/3 pi r cubed. Get me the volume here, or give me the radius. So the volume, 36 pi. We're plugging that in for V. 36 pi equals 4/3 pi r cubed. If you know r, you know surface area and volume. All right, what do we see on both sides? 10, what can I get rid of right away? Pi, gone. 36 equals 4/3 r cubed. All right, what would be your next move here algebraically? What's our next move? 13, next move?
Divide by 4/3.
Yep. Or if anybody wanted to multiply by 3/4, I don't care. Both are going to get the job done. Excuse me. Both are going to get the job done. Divide by 4/3, multiply by 3/4. Either way, what do you have r cubed equal to? 8. What do you have it, Sophia? Just r cubed.
Is equal to 27.
27, good. We have talked about this now in this unit. It's not squared, so I don't want to take the square root. It's cubed, so I take the cube root, again, located on your math button on your left-hand side. Right? If you want to take the cube root, hit your math button. So when you have the radius length, let me know. 4 radius length. What are you typing in your calculator?
Wait, wait.
Cube root of 27. That's all I need.
Is that thing? Wait,
Go to math.
I didn't hear like what you said about
Cube root,
calculator.
left-hand side.
3.
All right, there we go. I feel like we should be done, but we're not, right? We're not. Now I got to go find the surface area. So now I have to go back to 4 pi r squared. And let's leave it in terms of pi again to make our lives easier. What's the surface area? Also happens to be 2 in terms of pi.
3 pi.
Where'd you get the 3? 4 pi times 3 squared, right? So I got to do 4 times 3 squared.
36.
36 pi. Now I don't want to. Oh, it's the same. No, it's not the same. Volume and surface area totally different. Remember, volume is on the inside, surface area is on the outside. So they don't end up being the same. Plus, these are squared units. Not the same. Questions? All right, you guys know we gotta do some heavy-duty word problems here. So how about these volleyballs? You guys read it through. I'm gonna let you go in a minute here to finish this on your own, but I just want to make a point. So you got partially inflated to fully inflated. How much does the radius increase of the volleyballs? All right, so let me just do partially inflated real quick. We're doing volume, right? Volume. 4/3 pi r cubed. So partially inflated, it looks like it's what, 180? And we're comparing it to its radius. All right, I'm going to let you go after this, but I just want to make a point. Notice there's no pi with the 180. Don't cancel it. Can't be canceled. All right, cannot be canceled. So you guys can divide both sides by pi and then write out that decimal, then multiply by 3/4. It's up to you. You can get rid of the 4/3 or get rid of the pi first. It's your call. All right, but you cannot just cancel out the pi's. So I'll let you guys go finish this. Find the radius of the partially inflated, radius of the fully inflated, and see what the difference is. All right, how much did it increase by? Do not drop any decimals. Don't drop any decimals to the end. So write them all out for the radius at the end. Write them all out.
C.
What?
Answers are double here.
Double mine, huh? So what'd you do?
Like that 3/4.
Did you divide by pi? You gotta get cube root, you gotta get r cubed all by itself. So you gotta get rid of the 4/3 and the pi before you do cube root. Okay? How's everyone looking here? Rounding to the nearest tenth at the end. Regents question right here, by the way, as well. We got this all in old Regents. Can we not get this? We okay?
I didn't get that for the first one.
So what did you do first?
Times 3.
Times 3? Okay. And then what?
5 by 4.
Okay. Then?
And then 5 by 5.
Okay. And then r cubed? Cube root?
Square root.
Square rooted?
No.
Should have cube root, right? Right? Because it's r cubed, right? So I don't want to take the square root. I want to take the cube root. Hit the math button, right? So you're good so far. Just got to go back and take the cube root of that number. Spence?
Good.
Yeah, darn right you are. Everyone else, we're all right? Okay, so what's the increase? 0.6 should be the increase when I subtract these two and round to the nearest tenth. 0.6 inches. We're all good. Let me know. Okay, next one. Little change here. Little change up. I want to introduce you to half a sphere, a hemisphere. Find the volume and surface area. Now, I know it may seem as easy as just divide it by 2, but there's a little catch. Let's do volume first. Okay, volume. All right, 4/3 pi r cubed off the formula sheet, but it is a hemisphere, so yep, we're going to have to cut it in half at the end. You're correct. Yep, that's fine. It's a surface area we got a problem with. I have an issue with them. Okay? All right, so let's go. 4/3 pi. Somebody hook me up with the radius length, please. Relax. Radius length. Kelsey, radius length. 14, good job. 14 cubed. Now, you could divide by 2. You can multiply by a half. It's not going to matter. All right, so divide that volume by 2. $5,747.0 to the nearest 10. Calculating that all right? Okay, everyone ready for surface area? Because I need you locked in here because it's not just going to be taking that surface area and divided by 2. There's more to it. All right, surface area. Let's get the formula out. This is what 4 circles you're responsible for. 4 pi r squared. No issues there. All right, yeah, we're going to divide it by 2 because it's a hemisphere. I only have half a sphere. But remember what surface area is. Everything on the outside, right? Everything on the outside. What you guys just did was this dome part. You took the surface area and divided by 2. That's the surface area of basically this dome part. Anybody know what I'm forgetting? Flip it up. You still got the bottom to cover for surface area. What shape is the bottom? A circle. Everyone agrees? So right now, this dividing by 2 is just the dome part, but surface area is everything on the outside. We didn't talk about the bottom, which is another circle. So be careful when finding the surface area of a hemisphere. Yes, you do divide it by 2, but you do have to add in that extra circle. All right, so be careful, surface area of a hemisphere. So 4 pi 14 squared divided by 2 plus the circle on the bottom, pi 14 squared. All right, so our surface area of a sphere, got to worry about the bottom as well. Don't have to worry about volume because volume's inside. I have 1,847.3 square feet. Anything before I go over my last concept here for today? So watch out, surface. There's going to be some on the homework tonight. Surface area of a sphere, got to count the bottom. All right, last one. Oh, Cavalari's principle. Ooh. Here's what it says. Even if two figures don't look the same, they could have the same volume. All right, even though they don't look the same, they could have the same volume. And here's why. Here's what the Cavalari's principle says. If you have the same height and same base area, same height and same base area of your figure, they will have the same volume. All right, same base area and same height. Let me show you. Look at these 3 pictures, I guess, right here. You got this nicely stacked one. You got the leaning one, and you just got the hot mess right here. They're all different, but they all have the same volume. Why? All have the same height. All right, all 3 of these objects right here, if we measured their height, would have the same height. And what shape is each base? What's the shape of each base? Just a what? Just a rectangle, maybe a square, but they're all the same, aren't they? If I calculated the area of this base, this square, and this square, they'd be the same. That's what Cavalari's principle says. Same height, same base area equals same volume. Let me drive this home now. 2 different prisms, but same volume, even though they look totally different. Why? Same height, and the area of the triangle is the same as the area of the the area of the rectangle. As long as it's got the same height and same base area, they have the same volumes. All good? All right, let me just throw these a couple examples at you and make sure we're good. I don't want you to find the volumes to prove to me. I don't. That's not the point of these 2 examples. I want you to use Cavalari's principle to tell me why they do or do not have the same volume. Do not calculate the volume. Don't calculate it. I want to use this principle. All right. First thing, do they have the same heights? These 2 prisms right here, do they have the same heights? 12, do they have the same heights?
Yeah.
They're both 13. They also have the same base area, capital B. So what we have to do now is calculate the base area for each for me, because there's two different bases here. Two different bases. Calculate the base area. Who's up here? 1, Anna, what shape is the base in this first prism?
Right triangle.
Okay, so I'm going to do 1/2. What do you got for me? Times 4 times 2. And that'll give me a base area of 4. What shape is the base in the next figure? 6. What shape is that base? So I'm going to do 4 times 1. Base is equal to 4. So we could say same volume, because they had the same height and same base area. And that's what Cavallari's principle says. You don't need to calculate the volumes. You can just have the same height and same base volume. Base area, sorry, not volume, base area. All right. As long as they have the same height and the same base area, you're good. All right, what about the cone and the cylinder? I think we can stop pretty quickly. Why? Same volumes here? 10, same volumes? Why not? They don't have the same? Done. We're done. I don't care if they had the same. I don't even know if you, it looks like it, yeah, they probably would have the same base area, but what I say? Volume's not equal. Different heights. Okay? Gotta have the same heights. And then the last one, which I got off a Regents exam. What about these stacks of quarters? Explain why the volumes are equal here using Cavallari's principle. Explain why they would have the same volume. All right, well, what do you have to have? Same height, which they do. All right, same height. And same. Do they have the same base area? Well, what is the base? What shape is the base? It's a circle, and they're all quarters, it says. So they have to have the same base area. I'm assuming all the quarters are the same here. All right? So same base area. Even though we didn't calculate it, we know it's the same base area because bases are quarters. Or circles, if you want to write circles instead. Okay? So I don't have a calculation to prove that the bases are the same, but I could tell you they're the same because they're all quarters. So even though this stack is a hot mess and that one's neatly stacked, they both have the same volumes. All right? And I know you're going to be devastated. This is your last assignment of the year out of the textbook. Okay, I know you're devastated. So if anybody has textbooks at home and you want to start bringing them in anytime, right? Because this is your last assignment out of it. Actually, no, don't bring them in yet because I did some review questions for the test out of it. So don't bring them in just yet. But this is your last assignment out of there. I know you're devastated.